In this class, we're going to look at discrete probability. We're going to go end to end, starting at the introduction to discrete, all the way up until binomial, which is a specific kind of discrete probability. Enjoy. Let's actually, I'll double check, make sure all the cameras, yeah, this one's blurry, but we'll wait till we need it, I guess. All right, so this one's going to cover some more probability stuff. So class 3 is having a probability theme. We're going to start looking at discrete probability. So what's going on here is, well, how this differentiates between other kinds of probability is that we're looking at things that can only occur in like very specific quantities. So one of the examples I give here would be like the number of ones rolled on a dice. You can only ever roll an integer number of outcomes, right? Like there's no possibility of rolling half of a 1 on a dice. You either roll a 1, a 2, so on and so forth. You have very specific outcomes. That's in contrast to continuous quantities. Typically these are around lengths of things. That's because length is kind of arbitrary where we cut it off as far as decimal places go. So you could say that something is 1 meter long, but maybe that's a bit of an approximation. It's probably closer to 1.02 meters if you really measured it. Or if you measured it a lot more accurately with like a microscope or whatever you do to highly accurately measure lengths, you might find it has a lot more decimal places. And one of the things we find is that you could basically go on forever as far as the number of decimal places go. And so for that reason, that would be continuous quantity. It's something that you can go to arbitrarily high precision. That would be continuous. But we're going to look specifically at discrete probability, so the specific outcomes. A lot of the time, when you're doing discrete probability, it'll come in the form of a probability distribution table. And those would look at something like this. You'll see some capital X, some little x, a bunch of different values for those x's, and the probabilities of those outcomes occurring. So capital X is known as the discrete random variable. That's basically just going to be a stand-in for the quantity that you're interested in. So if it was dice rolls, then capital X is going to be the variable that holds the dice roll, what it was, 1 through 6. Little x are all the potential outcomes of your experiment. So if it was the 6-sided dice, you'd have 0 to 6. In this case, it's, well, whatever this would be. Whatever could potentially be between 0 and 3. That's what little x is. So these are all these columns are basically different outcomes for your random experiment. And then all of these are just probabilities of those things occurring. So probability that capital X is equal to 0, or 1, or 2, or 3. All the normal probability rules still apply here. So all the probabilities have to be between 0 and 1. None of these individual cells will ever be greater than 1 or less than 0. They should also all add up to 1. So a probability distribution table should cover the entire expanse of possibilities. So every probability in that table should add up to 1 for it to be valid. And another thing that you find that is quite effective here are complement probabilities. This being that you can do 1 minus the complement to figure out the actual probability of something occurring. We'll see an example of that in a bit. Okay, so how do we actually fill a table like this? So an example I have is a jar which contains 4 white and 6 black balls. 3 balls are drawn at random with replacement. From there, we're going to create our probability distribution specifically around white balls. So this table is going to be around how many white balls could potentially be selected if 3 balls are drawn at random with replacement. So this will be a keyword that comes up a lot, this idea of with or without replacement. What with replacement means is well, I guess in this case, it'd be like as if you were picking a ball out of the jar, looking at it, seeing, yep, I picked a white ball, putting it back in, shuffle it up, and then pick another one. So it's basically like you pick it out, record the color, like write it down, put it back in, rinse, repeat. So the reason why that matters is because from trial to trial, as you pick more balls out of it, the number of balls isn't actually decrementing because you're putting them back every single time that you do it. And so for that reason, when you're calculating these probabilities, that matters compared to if they were continuously being removed. But okay, anyway, we've got to fill out this table. We know we're going to do from 0 to 3 because those are only potential outcomes, right? In 3 tries, you could pick either 0 white balls, in which you picked all black. You could pick 1 white ball, in which you could do a whole bunch of combinations there. Same with 2, and then 3 would just be all white balls. So little x being 0 would specifically mean only drawing black balls, because remember, this has to be, or at least it was told, to be created around selecting a white ball. So from there, only drawing black balls. First, let's just figure out what the probabilities of drawing each of those are going to be. There's 4 white and 6 black. That's a total of 10. So if you have 4 out of 10, that's going to be the probability of white. 6 out of 10, probability of black. Now, what I said earlier, the fact that the number of balls isn't decrementing from trial to trial means that we can just reuse these probabilities over and over again. So if you want to draw 3 blacks, you just stack 6 out of 10s 3 times. These are things made in sequence, which is why they multiply rather than add. And obviously if they added, they'd go greater than 1 anyway, so that's a nice little fail-safe for you to definitely not do it the wrong way around. But okay, multiply them all together. 27 over 125, or if you want, you can chuck a decimal in there if you have a CAS, or if you hate life and want to convert your fractions to decimals by hand. Yeah, you just repeat this a bunch of different times. It gets a bit fancier for the x equals 1, x equals 2, because now the number of combinations, this is where like your counting methods could come into play. But when you have these kinds of things, if you don't like your counting methods, well, the first recommendation would be get good at them. But on the day, if you're like, nah, I don't want to do your counting methods, there's not that many combinations to keep track of. You can just sort of imagine all the different scenarios there. So if you're picking 1 white ball, that's what little x being 1 means. You select 1 white ball. There's a few different ways you could do that in a particular order. You either pick it first, second, or third. And so when you do your multiplications through, you'll find that because it was with replacement, these are all the same number. Doesn't matter what order you do multiplications in, you get the same number anyway. So really it's just do one of them and then multiply it by 3. X equals 2, very similar. In fact, literally all that's changing is whites and blacks. It'll be the exact, sorry, not the exact same. It'll be different probability, but the exact same idea, which is you either put a black in the first, second, or third spot. And then, oh, that's really annoying. I thought I got all these italics. Damn it. Anyway. Yeah, 0.288 for that one. And then x equals 3, well, that's a nice and easy one. All whites, so 4 out of 10s stacked on each other. And then you just put them in the respective spots. At the end, you just want to make sure that all your probabilities add up to 1. That way you'll be able to check any errors that you might have potentially made. Doing that addition isn't the end of the world. It doesn't take that much time, and it gives you peace of mind that you've filled it out correctly. Anything I should clarify there, let me know. Otherwise I shall move on to another kind of question. Well, let's take a quick pause to drink. Okay, probability over an interval. So what we just did was fill a table up and figure out the probabilities of any given outcome occurring. So if I said find the probability that x was equal to 1, it'd be this. Right, it's just directly look it up on the table. We've done good. If I said find the probability that x is greater than or equal to 2, now you're dealing with a range of probabilities. Not that bad. You just identify what the interval is, so inclusive 2 and greater, which means you want to hit 2 and 3. All you do is just add them together. Nothing too crazy. So x being greater than or equal to 2, start at 2 because it's an equal sign, and then add the 3 all the way to the right, however far it goes. this is where complement probabilities become quite handy. So we want to find probability that x is greater than or equal to 1. We don't know any of these, and I haven't told you anything about the experiment. So there's no way for us to solve what these could potentially be. But we do have this initial value here, the fact that little x being 0 has a probability of 0.3. From there, because this entire table has to add up to 1, it means that everything in here must be 0.7, right? Because you've got 0.3. What plus 0.3 gives you 1? Well, that's going to be 0.7. What that looks like mathematically speaking is that you can change this inequality, saying x is greater than or equal to 1, and you can flip it by saying 1 minus everything that's not part of this. So this is everything that is part of the inequality. Complement probability says you can do 1 minus everything that's not, which would just be this. So if, for example, this said x greater than or equal to 2, you could do all of this, or 1 minus these two. So whatever's not included, 1 minus that. Now, obviously, in this example, you couldn't do 1 minus like this, because it doesn't exist, but in other questions, yeah, probably. That's that one there. This is where it gets significantly more interesting, because now this is where we start crossing over into different areas of study. So here's a nasty table. It's worth pointing out here, x doesn't necessarily have to be all like in a particular order, like they don't have to be sequential. They can be disjointed. And that's simply because x is the possible outcomes of an experiment. The typical example that I give here is like a gambling situation where it's like you have some probability of losing $1, some probability of gaining $1, and then some probability of gaining $10. Those outcomes would be -1, +1, and +10. So it depends on the experiment. You can have these sort of disjointed looking things. One moment. For those who are recently joining, I am a little bit sick, so I might take some pauses here and there. Okay, so the basic example, the idea here is that you have variables in this probability table. And so basically, you pretty much always start this one out by adding everything up to equal 1. Right, that's a fundamental rule of how probability tables work, and so adding them all up to 1 is a pretty good idea. From there, do a bit of simplification, and you'll come to a scenario where you'll notice you have a quadratic, right? So if you get everything onto the same side, you'll realize, this is a quadratic formula type thing. Or, if you really wanted to, you could do the factorization approach, but me personally, even though I'm decent at doing the cross product for factorizing, it's kind of like you're not guaranteed to find a couple of factors, so I'd rather just go straight to going into quadratic formula at that point. This one does show you that yes, you would have found some factors if you did do your cross product approach, but kind of hard to tell. You could do discriminant to figure it out if your discriminant is a perfect square or anything like that, but at that point you're already halfway done with the quadratic formula, so you might as well finish it off if you feel me there. But yeah, so just solving for p in that way, you've got two possibilities. Probabilities have to be positive, so you're only going to take the positive in this case. Now, minor nuance here. P is not a probability, it's a coefficient. Like all these are something times p, or p times itself. It's actually a coefficient. So just because p is negative doesn't necessarily mean that the probability is negative. Like this example here, p squared, if p is -1, -1 times -1 gives you +1. So p doesn't necessarily mean the probability is negative. Granted, I've never seen it be an issue. I've never really seen a situation where p being negative still meant probabilities are positive. I'm sure if we put like a negative sign on all of these, it might look a bit different, but point being, just keep that in mind, I guess. The slight nuance between there. So don't just immediately assume p is positive. That's about it there, really. yeah, quadratic formula, a bit of cross-discipline stuff. If you have any questions about that one, let me know, because that one definitely is on the tougher side, or at least this is about as tough as it does get. But okay, if not, next up, solving conditional probabilities. So I don't know how many weeks ago it's been now, but we've looked at conditional probabilities before. You're always going to start with the conditional probability equation, right? Which means you want to find the intersection of the two things. So you want to find the intersection of x being greater than or equal to 1, but also less than 3. And you want to divide that by the conditional, which is just whatever's on the right-hand side there. So as far as simplifying that intersection of things, if you can't immediately understand what's going on there, drawing a kind of number line like this can be helpful. So x being greater than or equal to 1 is the first portion of that, and so you would draw from 1 to 3. Remember, it caps out at 3 here, which is why we cap it out there. X being less than 3 means you're actually going to start at 2 and go down to 0. Less than is non-inclusive, and because this is discrete, it wouldn't be anything in between 3 and 2. The next valid answer would be 2, which is why this bit here is x less than 3. And then as far as an intersection goes, well, you're literally just looking to see where they overlap. And the only overlap spot is going to be from 1 to 2 there. So that whole thing up the top there can be rewritten as just x being between 1 and 2. This gives you two things to solve. You need to figure out the numerator, and you need to figure out the denominator. Numerator is x being between 1 and 2. As I said before, you just add the probabilities in your interval, and that's your answer. So these two added together, that's what that is. And then x being less than 3, you have a couple of options. X being less than 3 would be meaning to add all of these together, or you can do 1 minus this. Usually subtraction is a bit nastier. I think most people would prefer to do the addition of these three rather than one subtraction, but just showing you that you have two different options there. Because again, that's the complement probabilities approach. But either way, you have your numerator, you have your denominator, you just got to simplify that down. As far as going from decimal to fraction, literally all you're going to do is multiply top and bottom by 10 until there's no more decimals. Then you'll get your fraction like you want. That's all that is there. Because you definitely don't want to have decimal divided by decimal. That's not a... I mean, it's correct, but not a solution that would be accepted. Oh, and this one isn't capitalized either. Bugger. It's two typos. If you see any typos in the notes, let me know. I really hate them. I want these to be good. But anyway, that's that. Anything to clarify there? Let me know. Otherwise, we'll start looking at statistics after I take a sip of water. Alright, statistics. So pretty much across the board, when it comes to probability, it's going to be mean, variance, and standard deviation that you care about. For those of you doing general, you've probably already seen these. And even Unit 1 and 2, people have finished that, would have seen... yeah, all of this actually. If you've done Unit 1 and 2, you would have seen all these. Anyway, let's have a look. So, mean, sometimes called the expected value. The equation looks super nasty. This is mathematically how it is expressed. As far as what you actually do here, it's for those who know, it's the weighted average, or the weighted sum of all these values. What that means is you look at the x value, you multiply it by the probability. You look at the x value, you multiply it by the probability. And you keep going until you reach the end of the table, and you just add all your results together. That's what this means. So the 0 times the 0.216 plus the 1 times the 0.432, so on and so forth. Simplify, simplify. So as far as how to interpret this, if you see something like this in the future, this sum symbol, that's what that means. It's the sum. This thing here is an index. It just means what x value you start at. So x sub I, like I0 would mean, I being 0 rather, would mean x0, x1, x2, x3, and then probability of x0, x1, x2. And then it just means go up to n, where n is the end of the table. So this one would read, n would be 3, I would be 0. That's what that would look like. Don't really need to know that. It's more so just if you see it again, you'll know it's not the end of the world. Now, what did we actually do by calculating that? Well, we're basically seeing where the average result is going to be, or weighted together. So we can say that approximately all the data, or whatever the probability is centered at roughly 1.2. Now, that's not a perfect representation of what the mean is, because there are things that could make that weird, but it's a statistic that can help us, right? Ideally, you'd be using all these together to get a really good idea of what's going on, but this on its own tells you roughly where the center of your data is. And you can kind of tell that already, right? 0.432, that's the biggest probability out of all of this. And you can see more probability is to the right of this than it is to the left, so it's going to be slightly skewed right, which is why it says 1.2 here. That's what's going on there. Now, it can get a bit more complicated. So we saw e of x, sometimes using the Greek letter mu for that. Sometimes it's not just e of x. Sometimes there is a whole function inside there. What it just means is you're still doing the exact same operation, but what you're going to do is, instead of going direct for x multiplied by probability, you now do 2x plus 3 multiplied by probability. So this will be 2 times 0 plus 3 multiplied by 0.2. 2 times 1 plus 3 multiplied by 0.15. And like, you can see how much hell that would be to write out, but you know what, that's the cards you dealt at that point. This is pretty uncommon, but I wouldn't be surprised if it shows up potentially on a SAC, because on a SAC it's very targeted stuff, and so much more likely to be hit than on an exam, which has to cover like a broad range of topics. As far as a shortcut, so, well, I guess before that, anything unclear about that, let me know. I'll take a quick pause. So that's one way of doing it. It's pretty long, but at least it's a lot more like the previous example. There is a shortcut if the inside of your brackets is linear, and that's this situation here. So if you have any linear looking like this with a coefficient of a and a plus b, what you can do is you can take this coefficient out the front, and you can bring this plus b also out the front as an addition. So that leaves you with a situation where you're just solving e of x like you've done up here. So just regular old x times probability. And then multiply the whole thing by a, and then add a b at the end, which is what this looks like. E of x is 1.5 in this situation. If you were to just go multiply downwards from here. But because you want to do 2x plus 3, you slap a multiplication of 2 on there and you add a 3 to it. And that will also get you the 6, which is what we got from before. So up to you if you want to bother memorizing that. I, in school, never did like any of this. I don't imagine that changes, but this will at least, I know this appears in the book at the very least, so that'll at least prepare you for that. It's not super required. Yeah, and if it's non-linear, you don't really have a choice. You just got to deal with whatever's given to you. So this one's pretty common, e of x squared. This one will come up when you're solving for variance, which we'll see a bit later. e of x squared being square all these x values before you multiply them. So 0 squared times 0.2, 1 squared times 0.15. And you can see all those here. Add it all up just like you had before, e of x squared. It's going to be equal to 3 in this case. One moment. I did not actually click mute there. I was talking through that, yeah? I feel like I clicked mute the wrong time and now I feel like I'm off. Can someone like let me know if I actually was talking through any of this? I hope I was. Okay. Well, I know the recording definitely got it because it grabbed its audio from elsewhere. So I will continue. Anyway, variance. So, how variance works. A couple of ways you could do it. I'm not even going to bother talking about this one here because it, like look at this. Just no. Let's not even touch that. It's a mess. And so, better off is this version here, which is you're going to have, you need to solve it in two parts. You need to find e of x squared, which we talked about earlier, how you would do exactly that. And then you want to solve e of x all squared. So this just means doing the expected value like you normally do, x times probability, then square it at the end. This one, we just saw what that was like. So for this distribution, it's the same one from earlier. So we already knew e of x was 1.5, so e of x all squared means 1.5 squared. E of x squared, again, we did that one before as well. That was equal to 3. And so all we do is do the subtraction of those two things. That's it. So yes, you've got to do it in parts. It'll be more lines of working, but the lines of working will be significantly shorter. Like this one is just squaring your x values and multiplying probabilities. In this one, you're doing, yeah, you're doing the x value, subtracting the mean, squaring it, then multiply by probability. And you do that a number of times. And it's like, just forget it. Do it if you want, but not for me. All right, variance of a function. So again, this is the situation where you have something inside. Instead of just doing var x, it could be var ax plus b, or something like that. This one also has a simplification. So if you have any linear in there, which is as hard as it'll ever get, if they ever put anything beyond a linear in there, you might as well just skip to the question and go to something else because they've been really nasty. But do I have an example of both? No. Probably because the book didn't go any further than that. But if you needed to, you could treat it like this. But anyway, so as far as doing variance of a function, you can ignore the b entirely and just bring the a out the front as an a squared. I won't really get into theory as to why that is. It's kind of complicated. But we'll just take it as granted. So, as far as how you would go about this, I think this is the same distribution as before. Yeah, looks like it. So, using that linear simplification, instead of doing var 2x plus 1, you can now do, you can bring the a out the front. So that 2 is going to come out as a 2 squared. The plus 1 is going to disappear. So really we're just finding the variance and then multiplying it by 4. So we're going to find the variance, which means e of x squared minus e of x all squared, which we've done before. E of x was 1.5. You just do the multiplication directly. E of x squared just means squaring all these x values before you do your multiplication. And yeah, find those two values, do the subtraction, and that gives you the var x. but we didn't want just var x, we wanted this. So we're just going to slap a multiplier of 4 out the front, and that's going to give us a variance of 3, or at least a variance 2x plus 1 is going to be 3. That's all, really. Standard deviation is super simple. No matter what area of study you're doing, standard deviation is always the square root of variance. So literally everything I've talked about up until now, as far as variance goes, slap a square root on it, and you've now got the standard deviation. That's that. And then confidence intervals. So there are 3 confidence intervals they want you to be aware of. The only one I've ever seen come across, like be assessed, is going to be the 95% confidence interval. Now, a confidence interval is just a percentage likelihood that your outcome occurs between some range of values. So, for example, I don't know, if I was throwing a ball a certain distance, there's a range of possible outcomes. I could throw it 10 meters, I could throw it 100 meters, because I can throw a ball really far, apparently, in this example. But there's a certain likelihood that I throw it in any given range, right? And so 95% confidence interval just means I'm 95% confident that the ball is going to land somewhere between, I don't know, let's say 10 and 50 meters. Whatever. That's what this is all about. You've got your x value, which is the outcome, and it's going to be between some number of standard deviations. So what standard deviation, what variance, all those things are, those are measures of spread. It basically tells you how far apart your probability is distributed. So in if we look at this table here, this is going to have pretty low variance because the bulk of the probability is centered at x equals 2, right? Very little over here, and from there everything's getting a little bit. Versus if these were all like 50-50 split, if it was all like 0.25s across the board, well, then you're going to have pretty high variance because a lot of the probability is spread across the distribution. Now, what we're saying in this is that approximately 95% of the results are always going to occur between plus or minus 2 standard deviations. So you get your standard deviation from there, plus or minus 2 of those from the mean being the center of your distribution. 95% of your results should occur between that. 68 should occur between plus minus 1. 99% should be between plus minus 3. That's what that's saying. Now, for discrete, it's usually a pretty shit metric to track because it's better when you have a large number of outcomes, and we'll see why in a moment. So, same distribution. This time we want a 95% confidence interval. With that in mind, we need the mean, we need the standard deviation. So the mean, we've already calculated that a bunch of times. Same with variance. For standard deviation, we're just going to square root that variance. 95% confidence interval, you're going to have x in the middle, the mean, which is 1.5, plus or minus 2 standard deviations. So you just plug in the numbers into all the spots that you see, and this one tells us that our x value is going to be between negative 0.23 and 3.23, approximately. Now, that's obviously crap because, well, for starters, there's no negatives on this table, and for final, 3.23 is bigger than 3. So what this has told us is we're 95% confident that any of these will be hit. So basically, the metric is a lot better when the number of outcomes is larger. In fact, just to demonstrate that, let's see, do I have, probably, it'll be normal, maybe normal distribution. Let's see. Nah, not there. Continuous? Where's a good continuous? Where's a good one? Bugger, not there either. Alright, I know definitely one, which will be sampling and estimation. Confidence intervals. Okay. So here's an example of where it's slightly different, but not by much. So survey of 1,000 people, you've got some values that you're going to plug into your confidence interval. Basically, we're 95% certain that the proportion of people who exercise is going to be somewhere between 51.9% and 58.1%. So a lot more reasonable of a suggestion that the people who exercise are going to be somewhere either side of 55%. And because we had n of 1,000 different possibilities, that's where it became a lot more accurate. Okay, that's that really. Those are all the statistics there. Now on to binomial, which is a subset of discrete. So what binomial is all about is a special kind of discrete probability that meets these criteria here. So binomial means there can only be two possible outcomes. So basic example is going to be a coin toss, head or tail. That's why it's binomial. Binomial basically meaning two, right? One or the other. Repeated trials of the experiment need to be independent. So again, with the coin toss, if I toss a head on the first toss, the probability of tossing something on the second toss doesn't change because of that first toss. They're all independent of each other. We've already talked about what independent events would be like as well. So if you want to calculate that, you can, although a lot of this is just using a bit of common sense as far as what's actually going on in the scenario. And then probabilities shouldn't change from trial to trial. I used to think these two were basically the same thing. They're pretty much the same thing still, but it is a little bit different. So probabilities can change from trial to trial. Basically both of these can be different. You can have independent events and the probabilities change from trial to trial. It just means that something else is impacting them. But for binomial, you want all of this to be true. So they shouldn't change, should be independent, and there should only be two possible outcomes. Now, that can be a bit to remember. So as far as some keywords to look at for whether you have a binomial thing or not, anything where you have like with replacement or things are being returned, that's usually going to be binomial because the probabilities aren't changing because the sample size isn't changing from trial to trial. If it literally says independent, probably binomial. If you see this, definitely binomial. That is the syntax for a binomial experiment. It could literally tell you it's binomial, or even this idea of a fair trial, likely to be binomial, because it's talking about coin tosses a lot of the time. All binomial experiments can be solved with the Bernoulli sequence. So Bernoulli sequence is, you might recognize this part of it, that being the combinations or the selections equation. And then all you're doing is multiplying by some probability terms here. Basically, the probability of any given outcome can be given by this equation here. So in one particular example, we have a coin toss. It's being tossed 5 times in a row. We want to find the probability of tossing 4 heads. So to solve any binomial experiment, you need to know n and you need to know p. N is going to be 5 because n is the number of trials in the experiment. P is going to be 4 because, P is going to be 0.5 because the probability of getting a head is 0.5. Last thing to be aware of would be the little x. So we've got the n's in this equation, n, n, and n. We've got the p there and there. We just need the x. And so the little x is going to be 4 because you want to toss 4 heads. Plug them all in, simplify down, probability has been achieved. CAS syntax. So CAS can solve this. The syntax is just give n, give p, and then give little x. So on the, at least on the TI Inspire, it looks exactly like this. It will give you a decimal, so feel free to grab a copy of that and then grab a copy of this and then hit enter again. So to demonstrate that, I'll show on the TI Inspire first, and then see if I can find where I put it on the Casio. Menu 5. Hang on. Oh, I didn't actually write the shortcut. How nasty of me. Menu 5.5, binomial PDF. You're going to give number of trials, in this case was 5, probability of success 0.5, x was 4, and you'll see it'll give you a decimal, which not ideal, so just grab a copy of it, hit enter on it again, and then you got a fraction, if you want a fraction. As far as Casio, let's see what I can do. What did I? Oh, that's how I did that. My cord was getting caught on my phone holder. Okay, it's got to be an action. It's got to be. God damn it! Really? Yep, this is the part of the lesson where I try to remember where everything is. Come on. Advanced, interactive then. Distribution. Here we go. Discrete, and then binomial PDF. That'll be this one. It's another setup wizard. So they put things in a slightly different order because why would anything be consistent? X is 4, number of trials. At least they kind of tell you what it means. Number of trials is 5. POS, probability of success. That is a really weird wording on that. But anyway, invalid syntax. The reason why is because I had something there before. And I didn't delete it. Get rid of that. Again, it's going to be decimal. I think if you just pull it in and hit enter, it'll become a fraction, just like from before. So that's where you find that one. I did that in interactive, but I'm pretty sure it was also, yeah, it's also in action. Exact same spot. Oh, that's the difference. So interactive will give you a setup wizard, and action will force you to type it out. So I guess do the interactive version. Bit nicer. Anyway, that's that. Okay. This is a very talk-heavy lesson, this one. Might have overloaded this lesson. Let me know if this has been an overload. Maybe either personally or just chat now. But in the meantime, I shall continue. So, probability over an interval. So kind of like with the old discrete, which was just add all the probabilities in that sequence. You do the exact same thing, but because each of these are solved by Bernoulli sequences, you're now solving a sequence of Bernoulli sequences. So you do the x equals 0, 1, then you do the x equals 1, 1. In this case, we're trying to toss one or fewer heads. So that's why it'd be x equals 0, x equals 1. Add them together, and that's it. Cas syntax, so you're going to find those under a very similar spot. This time it's binom CDF, not PDF. So C being cumulative, because you're doing the cumulative. It's located in a very similar spot. You might have recognized it as being right underneath. So as far as Casio, that's your CDF there. This time you're going to get a lower and an upper bound because, well, it's over a range of values. Number of trials, and then POS. That's still weird. This one here, we want it to be between 0 and 1. So lower is going to be 0, up is going to be 1. Trials with 5. Not 5Z, but 5.5. Hit enter. Did it do it? No, okay, that's fine. I'll just hit OK. And then again, we're going to get that probability. It was a decimal once again, so just grab that. 3 out of 16, 3 out of 16, yeah. And then very briefly, on TI Inspire, menu 5.5B, so binom CDF. Very similar thing. Number of trials, 5. Yep, that's definitely a 5. Probability of success, 0.5. Lower bound and upper bound as before. Grab a copy. Same deal. Complement probabilities. So this is helpful for if you don't have a known upper bound. Well, more helpful for if you don't have a known upper bound. It's also helpful if you do, but the upper bound is nasty. Like if you want to do 1 or more head and you're tossing 5 times, doing that by hand, that will be doing x equals 1 plus x equals 2, 3, 4, 5. Or, better off, flip your inequality, do 1 minus x equals 0, and then solve one Bernoulli sequence instead of 5. A lot nicer. However, where this becomes a lot more nicer is when, well, still nice, basically, but we're not told n in this situation here, anywhere. We're told p is 0.25. N is what we're trying to solve for. And to do that, we're given a target probability, which is winning at least twice, so x being greater than or equal to 2, and we want that target probability to be summing up to 0.9. So, because we don't know where to cap out, we're definitely going to be using our complement probabilities here. So, instead of doing x greater than or equal to 2, the things that aren't in that interval is going to be the x equals 1 and the x equals 0. So you do 1 minus those. So, we're just going to expand those out. We have not looked at how to simplify when it's n's in these situations. So let's have a look at that. Yeah. If you have CAS, then by all means, just chuck it in CAS, of course, but as far as how you could do that by hand, that'll be a bit more important. So let's have a look. No, not a software update. No, I don't want that. Just this. Please focus. Maybe it'll start typing, or drawing rather. So, one of the first ones we have to simplify is n factorial over n minus 0 factorial, 0 factorial. 0 factorial. So, if you haven't done anything like this before, try expand it out to begin with. So, that might sound stupid. How do I expand that out? Well, you just follow the pattern. You would start at n, and you would go 1 less than n. Then you would go again 1 less than that. And so you would continue that pattern on and on. Or at least that pattern would continue on and on. As far as the denominator, this simplifies down to just n factorial. So it's going to have n factorial there. And 0 factorial is just by default going to be 1. That's just an identity. So what you're going to have is n factorial on the bottom. We've already got this pattern from before, which we know n factorial already is. So again, you're going to have n minus 1, n minus 2, and well, you can see these factors all cancel. So this is just going to go down to 1, which is why if you look again at the book, you'll see that that whole thing disappears. Power 0 also disappears, and well, you're just going to be left with 0.75 power of n. Gets a little bit different when you have n minus 1 factorial on the bottom to start with. So if I undo a little bit of this, yeah, put an n minus 1 in there and a 1 in there. 1 factorial is also 1, so you can still ignore that. But as far as expanding that out, numerator obviously hasn't changed, so you keep that as is. But n minus 1 factorial means you start at n minus 1 and then go n minus 2, n minus 3, so on and so forth. So what it means is when these cancel, you still got this n left over, which is why when you look back at the book, n is going to be at the front as a coefficient. So that's those. That's your x equals 0, that's your x equals 1. Put them into the spot and then plug it into CAS, because you're not going to solve this without a CAS. So chuck this whole thing into CAS. we're going to set it equal to 0.9 because that's our target probability. Right, so target probability being 0.9, set it equal to 0.9. Don't use an inequality. I know it says more than 0.9. Don't use greater than 0.9 because the CAS will just have a fit. It'll just say, no, not doing it. Use an equal sign and then use a bit of logic to figure out which of these would be the appropriate answer. So n, that's dumb. N being a number of trials, definitely can't do something negative number of times. But being a decimal is also kind of shit. And so in pretty much every case I've ever seen, it always rounds up. If you want to be absolutely sure, just try plug in 14 and 15 into your expression. It is CAS, so you should have this defined. So you do like a little define like that. And then you just plug in 14 to 15. That one's a little bit less than 0.9. That's a little bit more than 0.9. We wanted more than 0.9, so we pick 15. That's that one. That's simplifying that by hand. The CAS can just do that though. So if you tell the CAS to do it, it'll look something like this. So you start with your fraction. It'll be, I'll do the second one, which would be, I'm going to use x instead of n just because speed. It'll be x factorial on bracket x minus 1 factorial. That's an I, not a factorial. There we go. And then multiply by 1 factorial. It'll just do that. So obviously it says x instead of n. You would just put an n on your working out. So it just does that. Actually, I'm curious if the... Well, now I've said it, I've got to try it. I just got to remember where the factorial button is on this. Let's see if this one can do it. Okay, so I want a fraction first of all. I want to do x factorial. Where's an exclamation mark? Really? It's not going to give it to me, huh? Where? Symbol? Yeah, there we go. X factorial over bracket x minus 1 factorial times 1 factorial. This better actually be a factorial, not just an exclamation mark. I don't know if that's because it was an exclamation mark or if it just can't simplify it. I'm going to assume it can't simplify it. Well, actually, I can figure that out pretty quickly. If I put in x as some number, does it simplify? Yeah, okay. So Casio is just dumb. Sorry for those who have a Casio. Buy the TI Inspire, better off. Okay. That's that. Anything's clarified there, let me know. Otherwise, I'm going to take a quick pause. Still alive, let's go. So, statistics. These are actually a lot faster than the other ones. So you'll see statistics are pretty quick. You're pretty much only ever multiplying n and p as far as when you're solving a few things. So not so bad. So for example here, we've got another jar experiment, 5 white, 3 black. It is, yeah, being replaced. So binomial, right? It's being replaced. There is no changing of probabilities. Each thing is independent. And you only have 2 options. You have a white ball or a black ball. So we're selecting 3. Where is it? We're selecting 3 in total, which means our n is going to be 3. The probability of selecting a white ball, because that's the thing we care about here, white balls, is going to be 5 out of 8. So when we calculate our statistics, the mean is always just n times p for binomial. So we have n, we have p, smack them together. Variance, also pretty chill. You just put the mean out the front, and then you do 1 minus p. So nothing's actually changed there. You still know n and p for that. Standard deviation is always the square root of variance. So just square root it. So within very few lines of work, you can get all three statistics. These will be on your formula sheet as well, by the way. Don't have to memorize those. Okay. Sometimes you'll have the statistics first and have to get n and p from those. So what that ends up meaning is, in this case, we have a mean of 4, variance of 2. Well, again, it's just, instead of plugging in n and p to get mean and variance, you plug in mean and variance, and then you simultaneously solve to get n and p from there. Mean is always np, variance is always np, 1 minus p. From here, it's just doing some... I've done a substitution method here. Probably faster would be elimination. Doing a division of these two things would cancel the np's. So rearranging for p wouldn't be too hard afterwards, but if you like stock standard substitution, that's fine. That's all I ever really did when I was studying methods. Simultaneous, nothing too crazy there. Yeah. And then again, confidence intervals. Nothing's changed here. Still plus minus the same number of standard deviations that we've talked about from before. Maybe this one will make a bit more sense. Yeah, look at that. Here we go. An actually nice one. So, 80% of students attend public schools. We have a group of 400 people. We want a 95% confidence interval. So basically, I want to be 95% confident that some random group of 400 students is going to be, like, how many of those are roughly going to be at a public school. So from there, we want mean and standard deviation. Again, we've seen how that calculates. NP for mean and square root of variance for the standard deviation. Mean of 320, standard deviation of 8, plus minus 2 standard deviations. That means that any group of 400 students, I'll be 95% confident that anywhere from 304 to 336 of those people will be attending public school. And thus ends the hour-long lecture. Let me know if this was an overstuffed lecture. I know we didn't do any questions for this one, but it did mean we did a full crash course on all of Discrete. That's about it, really. We've got 2 minutes to spare, so if there's anything you want me to clarify, let me know. Or if you have any feedback, happy to take that. Otherwise, I'll let you enjoy the last 2 minutes. You can have those back. Take care.